everybody. Happy Friday. I wanted to be able to go over bridge and mini lesson with you, even though I'm not there. How cool is technology? Not that cool, but hey, here's bridge. You hopefully noticed that I gave you a reversible reaction that's in dynamic equilibrium, which means the rate of the forward reaction is equal to the rate of the reverse reaction. And I want you to look at the potential energy diagram I provided you for that reversible reaction to take a look at a couple of things that might be going on with energy and with heat, and just break it down a little bit further. So if we start with question 1, I'm just looking for the letter that represents a number of different things. So for part A, we're looking for the potential energy of the products, and that's just how much potential energy our products over here on the right-hand side of the reaction have. So I'd say that's represented by letter G. It tells us how high that particular, if my pen works, there it is, how high that particular line is on the diagram. Part B is asking us for the letter representing the heat of reaction, also known as delta H. And remember, guys, delta H is just how much heat entered or exited the reaction. So the difference in the potential energy of the products and the potential energy of the reactants. So how much potential energy was either, in this case, added or taken away. And that little distance is marked here by F. And for part C, we're looking at the activation of the forward reaction. So how much energy does it take to get this thing started in the first place? Well, that's going to be equal to the amount of energy we had to put in to breaking bonds. Remember, that's an endothermic process before the reaction was really able to produce the products it wanted to produce. So that height is represented by E. And it was notably important that I mentioned the forward reaction because we really can read this diagram going both ways, from reactants over to products, and then reverse reaction being from products back to reactants. And you'll notice that the reverse reaction has an activation energy too, and we're going to label it on number 2 by saying it takes this much energy from here up to the very top of my graph to activate the reverse reaction. So the activation energy of the reverse reaction is shown there. And you can see for this particular reaction, the activation energy of the forward reaction is greater than the activation of the reverse reaction. What we're looking at for number 3 is whether the forward reaction is endothermic or exothermic. And you guys have done this forever. You know that when the graph ends higher than it started, we must have taken heat in, making it endothermic. Reading it in the reverse direction is no different, folks. So we start higher than we end when we're going in reverse. So heat had to exit from going here down to here, making it exothermic. For question number 5, it's asking about the effect of a catalyst on chemical equilibrium. So first I want to draw in what a catalyst would do. Remember, it's just speeding up the rate of reaction by making it easier to get from reactants to products. So I'm going to lower the activation energy of the reaction so that it's easier for particles to collide effectively because the catalyst is bringing them together. Now, if you notice, that does lower the activation energy of the forward reaction, but it also lowers the activation energy of the reverse reaction. So that's going to make both reactions take place at faster rates. So it really doesn't affect the state of equilibrium, but it certainly does increase both the rate of the forward and reverse reactions. So ladies and gents, if at this point you have any questions on bridge, anything that I said that was just nonsense, go ahead and pause the video and ask any questions that you have now. All right, well, I'm going to jump ahead to mini lesson where we're going to really think about what it means to be in dynamic equilibrium and how we can change what equilibrium looks like for a reaction. So in order to get something into equilibrium in the first place, you better be part of a closed system. And you can see there that there are 2 drawings representing both a closed and open system. When you're in equilibrium, the rate of the forward reaction has to be equal to the rate of the reverse reaction. Well, here I could see both products and reactants being able to collide, so you'd be able to have both a forward and a reverse reaction, provided your reaction was reversible in the first place. But over in this open system, maybe this is hydrogen gas, like what you guys saw with the metal and the acid the other day. It's all escaping out into the atmosphere. There's no way we could shove that gas back into the container to try and get it react and provide the stuff for the reverse reaction. So open systems just don't work when it comes to equilibrium. Now, let's say you have a beautiful little closed system and you've made it so that it's in a state of equilibrium. In any possible state of equilibrium, there are 4 things that are going to stay constant or the same over time. And we know in an equilibrium state, our rate of forward and reverse reactions are the same. That means we can't change anything that would alter the rate of the reaction. You guys have done this before. You know how to speed up a reaction to make it go faster or make it go slower. We've seen that catalysts are one thing that don't have an effect on equilibrium, but there's other stuff that does. What if we tossed in more reactants? That would certainly affect the rates of reaction. So in equilibrium, that's going to stay the same. The concentration or amount of the reactants is going to be constant at equilibrium. And sometimes you'll see this written with brackets. So if I use R for reactants, I'm going to put brackets around the R to represent the concentration of reactants. That's not changing over time, provided that the system is in a state of equilibrium. Same deal for the products, right? If I tossed more in there, I would start shifting or moving away from a state of equilibrium before I could restabilize. So at equilibrium, the concentration of products also remains the same. And again, with the brackets, we could just represent that as concentration of P. You guys also know that changing the temperature can affect the rate of reaction. So at equilibrium, we can't be changing the temperature. Same deal goes for pressure. We cannot change the pressure, otherwise we'll change the equilibrium state. So your lab today, guys, during workshop has to do with what happens if one of these things changes. Do I try and make more products? Do I try and make more reactants? Your system is going to try and compensate for the change that you make in order to get back to its happy equilibrium state. So read carefully as you're working. Ask lots of questions when you have them so that you feel like you're doing things appropriately and safely. The materials you're working with today are toxic. So please, please, please bring your best lab behaviors with you as you work. If you have questions, there are lots of capable people in the room that are going to be able to help you. So hopefully at the end of the lesson, you're feeling confident about observing and maybe trying to explain why we see certain shifts towards a higher concentration of products or a higher concentration of reactants when one of these 4 things is changed. So good luck, everybody. I look forward to seeing you again next week.